Welcome back, students. This is where we stopped in the previous video, but let's have just a little bit of recap. Okay, this is a given ordinary linear differential equation with variable coefficient, and we started with the power series expansion of y of t and the derivative y prime of t and y double prime of t. Put those into the original equation with appropriate color coding so that you can see things better. And then some algebraic manipulation to break up parentheses, and then push all the t's inside so that you get summation and nothing else. And then we do some index shifting. Change first two series, blue and red, to t to the nth power, generating this equation, and then make the first and third series begin from n equals to 0. No problem there because adding extra 0 doesn't change anything. This is typical for regular singular points. Getting coefficients together, we get the recursive relation, and solving for the most recent term, Cn plus 2 term, you get this recursive relationship. Okay, that's where we're going to begin. Okay, this is the recursive relation we got. Let's make it a little bit larger. Okay, all right. Okay, here, let's begin with n equals to 0. So this is C0, and this one is becoming C1, and we have 0, 0, 0, 0, and 0 there. What do we get? We get this computation there. And what do you see? 0 times this, so this part just drops out, and we get this simplification, 1/2 C0. It'll turn out 1 over 2 factorial, but at this moment it's a little bit hard to see. Let's go to the next step. Plug in n equals to 1, so that this is C1, this is C2. What do you get? We have 1 minus 1 here, so that part just drops out. And then the C2, we already found out, 1/2 of C0. So after some simplification, what do we have? 1/3 times C2. So in the end, we get 1/3 times 1/2 C0. Total, we get 1/6 of C0, but it'll turn out 1 over 3 factorial. Still, it's a little bit unclear whether you get factorial or not. So let's go over to the next step. Go to n equals to 2. So this is C2, that's C3. All these are now 2's, and we get that. Some simplification here. This is 2 times 3, so 6 times C3, and this is 1/6 of C0, so we have nice simplification like this, and in the end we get 1 over 24 of C0. 1 over 24, it's actually 4 factorial. 4 times 3 times 2 times 1. Maybe from here you can see the pattern, but if you still don't see any pattern, maybe you'll have to do it once more. If you never see any pattern, in that case, just leave several steps and then just move on, because nobody actually cares about those kind of things. As a matter of fact, this is one of very exceptional case that we have really nice answer. So we actually are looking for the pattern, but most of the time in series solution, we're not looking for pattern. Once you have this recursive relationship, you just put in the computer and then let the computer handle first 1,000 terms and do the computation. You get really, really accurate in terms of very small error term. Anyway, in this case, our working theory is 1 over n factorial, 1 over n factorial, 1 over n factorial. And let's see if that is really the case. So Cn is this one using the previous recursive relationship over here. And let's apply our theory. This C of n plus 1, as a matter of fact, excuse me, I rewrote this. I did some index shifting here. Excuse me, let me explain that index shifting. Okay, let me explain that index shifting here. Here I replaced n by n minus 2. So this becomes n minus 2. That becomes n minus 2. That becomes n minus 2. N minus 2. Okay, if you do that, and if you simplify, you're going to get this. That's how you get Cn expressed in terms of the two previous terms. Here, Cn plus 2 explain Cn plus 2 written in terms of two previous terms. Here, Cn written in terms of two previous terms through the index shifting. And apply our hypothesis. Cn minus 1 is actually C0 over n minus 1 factorial. If you have n minus 2, then we need n minus 2 factorial down here. And then let's do some algebra. N minus 1 factorial is n minus 1 times n minus 2 factorial, so they cancel each other out. So we have n minus 2 factorial only. And then n minus 2 minus n minus 3, if you simplify, you're going to get just 1. So we have what we want, 1 over n minus 2 factorial, and times C0. And what do you have before? N times n minus 1. Put everything together, then what do you get? We have n factorial down below. So yes, we can prove this hypothesis inductively like this, but if you're not really interested in the proof, then you can make some educated guess through first several terms, and that is okay most of the time. Okay, let's put those into our final form format. This is C0 t to the 0 power, so that's constant term. And then we have, starting from n equals to 2, we have this series expansion. So this is C2, C3, C4, and so on. Those are all C0 over n factorial. And then final C1 is arbitrary, so we have C1t. And what do we have here? We have 0 power, and then all these begin from the second power. The first power is missing. So let's borrow that from this part. How do you do that? C0 over 1 factorial. Add them over here to get this series, and then subtract over here. And this manipulation, actually it's not really that important as a matter of fact, because they're going to become arbitrary constants anyway. You see, this part over here is nothing more than just exponential function. You can clearly see that, I hope. So that we have e to the t power times a constant. And then whatever that is, it's an arbitrary constant anyway. So we get this form, a e to the t power plus bt. Okay, is that really true? Can we check through Mathematica? Yes, we can. Let's run this program. So I just name it as, I just name my function y of t as a e to the t power plus bt, as you see in the second line, same as that. And then let Mathematica to simplify the differential equation. T minus 1 y double prime minus ty prime plus y. What is this part? It is nothing more than the left-hand side of the original equation. Let us simplify. And yes, Mathematica simplified, and what did you get? We got 0, which means, yes, we're looking at the correct solution here. That's one way to verify. Another way to verify, it's a little bit trickier. I'm using the dsolve command, and then we get this differential equation is equal to 0. And then you're looking for this function with respect to this independent variable, and you're going to get an appropriate solution. And indeed we have e to the t power times some constant minus t times some other constant. What did we have before? We get plus some constant times t. Here we have minus. Doesn't matter. No, not really. It doesn't matter because this is arbitrary constant anyway. So we can just push the sign inside. So there's no difference there. So in any case, this is a good verification. I do not really recommend the desolve command. It's tricky, but the previous simplification, it works like charm and is a good way to check your answer. I do recommend.